it's my pleasure to introduce Madeleine Udell today. Madeleine is Assistant Professor and Richard and Sybil Smith Suspicion Tenure Fellow in the Department of Professional Research at Cornell University. She did a PhD in Stanford University, and she is working in the intersection of optimization and machine learning, and on other problems in matrix optimization and efficient algorithms for past 30 years later. So, thank you.
It's a pleasure to be here today to a room-breaking crowd. I'm here to convince you that big data is low rank. And I'm going to do that in two ways. I'm reversing the order of topics for my abstract. First, I'm going to overwhelm you with applications of low rank matrices that get weirder and weirder, and you're going to start wondering why it keeps working. And then I'm going to tell you a theorem that maybe will explain to you why you should have expected that all of these big data matrices look low rank. Okay, let's get started. So this was one of the first applications that I saw where these ideas became important. This is a large data table. I'm showing you 4 rows and 5 columns, but you can imagine it having maybe hundreds of millions of rows and tens of thousands of columns. In here, it's a data set about people. So we know various things about these people. We know maybe their age, their gender, maybe what state they're from, their level of income approximately, their level of education. But there are a couple things that you should notice about this data set. One is that we have not observed all of the values. Some of these entries are missing. The second is that the data is of a variety of different types. Okay? So some of these things are numbers. Some, well, in this data set, these are encoded as a Boolean. The states are, I think, 1 of 50 values. The income, well, that's a positive number, but maybe you shouldn't think about the distance between $100,000 and $101,000 the same way as the distance between $10,000 and $11,000. Okay? And level of education, which are ordinal variables. Okay? So suppose we'd like to do some basic data analysis in a setting, like we want to figure out what are the demographic groups, right? Who's similar to whom? We want to find typical responses within those groups. We want to identify features that are related, right? Maybe you could predict one of these from another. We want to impute missing entries and figure out what's the gender of this 57-year-old from New York. Okay? All of these are really challenging in this heterogeneous data setting. Okay? We got a huge problem. We have different kinds of entries. And many of them are missing. What do we do? So first we generalize because we're mathematicians or applied mathematicians. And so more generally, suppose I've got a data table, which I'll call A, has M rows and N columns. So think of the rows as examples and the columns as features. Ith row is the feature vector for the ith example. The jth column gives the value of the jth feature across all the examples. If we're going to solve this problem, we're going to need to make an assumption. And in this talk, we're going to make a low rank assumption. So what I mean is, we're going to try to approximate our data table A as the product of a skinny matrix X and a fat matrix Y, where the inner dimension is K, which is a parameter. That's going to be the rank. Okay. So on the left, you can see X times Y. These are both numeric matrices. So this is a low rank numeric matrix, rank K or less. On the right, this is a data table with heterogeneous entries and missing values. Okay, so we have to explain what squiggly equals can mean, right? Because otherwise it doesn't make sense, okay? But if we can figure out a good meaning for squiggly equals, then my claim is it would be really great. Because we have one row of this matrix X, that's a collection of K real numbers for every example in our data set. We'd have a collection of K real numbers for every column in our data set. So you can think of these as k-dimensional representations of the examples and of the features.
So
yes.
I guess you're going to get to this perhaps, but when you say data table A,
yes.
You're not assuming these are taking values in the real.
No.
Okay.
Yeah. Okay. Right. So you can think of these X and Y as a compressed representation of this data set. You can think of these X's and Y's as points associated with the examples and the features. Okay? And you can also approximate entries by looking at the inner product between xi and yk. Here, in this whole talk, xi is a row vector. So little bit weird, so this is an inner product. Okay, so why would you do this? Number of reasons. One is compression. Okay, you can reduce the storage cost of your data table or speed transmission. One would be to understand your data set. You could cluster or visualize these rows of X or columns of Y. That's easy to do because they're real valued vectors. You might be doing this to remove noise by looking at the entries of the imputed matrix X times Y rather than the original entries A. You might be doing this to infer missing data or simplify data processing. We'll see examples of all of these in this talk. So, how do we do it? In this talk, I'm really spending much more time on understanding when low rank pops up and less on optimization. So this is going to be a very short introduction to how to fit these models. If you want to know more about that, I would be very happy to talk later about how to fit them. Okay, the simplest case of fitting these low rank models is principal components analysis, and I'll bet most of you in this room are familiar. So there it says, if A is not a data table, it's a real valued matrix where all the entries are known. Okay, then why don't I solve this problem? I'll minimize the distance between A and X times Y in the sense of the least squared error. So people have been doing this for over 100 years, and there's a very good reason, which is that there's essentially an analytical solution obtained by via the singular value decomposition. Okay, the truncated singular value decomposition. So take the first K singular vectors on the left and right, the first K singular values, and that gives you a solution X times Y to this problem, which you can factor however you want. Okay. What's more interesting for other applications is the fact that there's also a solution by alternating minimization. So what I mean is, guess an answer for Y, minimize this objective over X. That's a least squares problem. Really easy, fast to solve, parallelizable. Okay, now fix that guess for X, minimize over Y, and repeat. Okay, go back and forth. You can show that with probability 1 over your initial choice of Y, that converges to the global optimum. Okay, so alternating minimization with probability 1 works for PCA. And it's going to generalize much better to the problems that we're interested in. So, what's the generalization? There are 3 generalizations that we need to make to treat generic heterogeneous data sets. Okay. One is that rather than minimizing the sum of squared error, right, I can't subtract a number from California, right, or from female. It doesn't make sense. Okay. So instead, I'm going to have a loss function that tells me how annoyed I am to have approximated that value, like California, by that number, 7.5, right? It's a real number. Okay. And I'll have different losses for different kinds of observations. So different losses for reals, for Booleans, for categoricals, etc. And I'm not going to have time to get into all of these losses, but they're really good ones that work well for imputation. Okay. The second change is that we're only going to observe the entries for ij in this observation set omega. Okay, so rather than minimizing this objective over all the entries in our matrix, we're going to minimize it just over the entries that we have observed. The third change is we're going to add these regularizers, and these are help constrain the solution. They provide better statistical power and statistical guarantees for recovery. They can also help with interpretability. Like you can say, please, I'm going to penalize given vector x unless it's very sparse or something like this. Now, once we made these changes, suddenly the objective can be NP hard to optimize. So that's bad. On the other hand, there are effective algorithms in practice. There are algorithms that have provable guarantees. But for this purposes of this talk, it's enough to note that the simple alternating minimization algorithm can still be run and still works pretty well. Okay? And what I mean is, right, fix y, minimize over x, fix x, minimize over y. It won't converge now provably to the global optimum, but it does pretty well, especially if you initialize it. So that's all I'm going to say about optimization for this talk. Okay. So the simplest settings in which you might want to do this is matrix completion. This is also a problem that's pretty familiar at this point. So you say, my observations are still real numbers, but I've only observed them for some index set omega, not for everything. Okay. In order to get better statistical guarantees, I'm going to add a little bit of regularization, quadratic, on both x and y. Okay. There are two regimes in which you might want to solve this problem. One is where some entries of the matrix are missing. In this case, you can interpret this as, one thing people will often do is they'll take the rows that have any missing values and just delete them. Okay. that's sort of silly, you're throwing away data. Okay? So instead you can learn from the data that's there. The other setting in which you might be interested in this is when most entries are missing. So every row has missing values. This is the case in, for example, the famous Netflix problem, right? No user, no movie watcher has rated all movies, or if they do, then it's junk data, right? In this setting, it's important that matrix completion still works, even if there's, right? You would throw away all your rows if you threw away the rows with missing data. One of the earliest theorems in this area said if your matrix A has a rank that's less than the target rank you're allowing your model, and you've observed enough entries where enough is like the rank times log of the dimension in each row. Okay, so every user is rated a constant number of movies times the log factor. And a couple of technical assumptions on the original matrix. The matrix completion exactly recovers the matrix A with high probability, okay, over this random model. So that's pretty good. Now in our setting, we've got more complicated data. So what do we do? One idea is to choose a loss function to maximize the log likelihood of the observations. Okay, so Gaussian, the log likelihood of that distribution gives you the squared error. Okay? But if you think your errors are not Gaussian, you should not be using the squared error. So if your errors are Laplacian, or actually more generally heavy-tailed, you might want to consider using the absolute value error. Okay? If they're Gaussian plus Laplacian, you can show the right thing to use is the Huber function. If they're Poisson, or if they're Bernoulli, right, they're associated distributions, negative log likelihoods that give you loss functions. Okay? So this is sort of a canonical formula. How well does it work? So this slide is a little bit silly. I'm giving you a template theorem. Okay, no one proved this theorem. But for particular instantiations of the parameters, like what is the probabilistic model, in fact, people have proved that matrix completion works for these probabilistic models in all of these cases. Okay, so there's like a very long literature. This is only very far from exhaustive at this point. Okay, but what I want you to take from these results is that you should have high confidence statistically that these approaches are likely to work, as long as you have enough observations that are random enough, and you're using a reasonable loss function.
So
yes.
So why does the previous theorem depend on the k prime and this one does not?
So that's just saying that the true rank should be feasible for your model.
Right.
This is actually a result for the in the convex case. So we're allowing any rank k. There's sort of separate literatures treating this as a convex optimization problem that's very slow to solve and memory intensive, and treating it as a non-convex problem. I'm eliding over that difference in this talk. A lot of the work that I've done on optimization is looking at the convex side and trying to figure out how to make those solves go faster and use less memory. But okay, that's a different talk. You'll have to invite me back. What loss functions might we use? Here's a zoo of loss functions that I would recommend. Okay, but you might get different performance with different loss functions. Okay, we should try to understand, do the loss functions matter? How do they matter in practice, empirically? So we're going to get to that in a moment, and I want to get there. Okay, regularizers, there are essentially four that people tend to use. One is to ask that the coefficients, right, that these latent representations have small norm. And this is generally what people are able to prove guarantees about. Also, it helps with optimization. One is to ask that they be sparse, often by penalizing the L1 norm of the representations. People will also ask that they be non-negative, which helps with interpretability, or even that they be clustered, that at most one entry be non-zero. So you can fit all of these kinds of models into this framework. And in fact, using this regularization, you can show alternating minimization reproduces the canonical k-means algorithm, Lloyd's algorithm. Yes?
So your setting is that you take the same type of regularizer for both, or because relative makes explain one regularizer and another one?
So right, here all the regularizers are the same except in this example. But generically, you can also imagine mixing and matching. Sure, yeah?
Why have you chosen these regularizers to act upon the rows of X
Yes.
and the columns of Y, as opposed to the other way around.
Yes. The
Like
reason
for these choices, it doesn't
Yes.
matter because
Yeah, for these choices it doesn't matter. The reason I've made that choice is because it ensures that the optimization, so if you do it in an alternating fashion, that the optimization problem minimizing over X is separable over the rows. And so it parallelizes much better. And same thing over Y. If the regularization is separable over the columns, then the problem is separable over the columns, and it parallelizes much better.
but the theory for global optimality is for the other kind.
The theory for global optimality is only for this case, right, sum of squared errors is decomposes, and so you can do it in either way.
I don't agree with that, but we can talk about it.
Okay, great, okay. Okay. So applications, why would we do this? Okay. So first I have to tell you about how to do imputation. Okay. Once we have these weird kinds of values, we can't just impute by taking the corresponding entry of X times Y, because that's a real number, and the thing that we have is something that's not a real number, right? The data is something that's not a real number. We need to be able to impute something like California. Okay, so how do we do that? The loss function once again tells us how to do that. Okay, so once I have a value for xi times yj, I can do imputation by minimizing the loss function over values for a. Okay, and that's implicitly constrained by the domain of L and its second argument. So if the second argument has to be a state, the outcome of this argument is a state. Okay, so it's sort of purely formal that I get imputations in the right domain. And you can check that for the case of losses that you understand, like quadratic L1 or Huber loss. Actually, the solution to this is just xi times yj. That's what you would expect. If the loss function is something else, so for example, maybe it's hinge loss. Okay, so 1 minus x times y, which I'm calling u here, times a, the positive part of that. You can check that the imputation is actually just the sign of x times y, which is what you would expect for hinge loss. Okay, so how well does it work in practice? This is a synthetic data set, but what I want you to imagine is that this comes from a hospital. Okay, every row of this data set, imagine it's a patient. Okay, and we've done 3 different types of tests on these patients. Some tests give real valued answers, some tests give Boolean answers, and some give ordinal answers. Okay, values between 1 and 7. Except this hospital had a problem in their information management system, and the results of 2 of the kinds of tests were lost for half of the patients. This is a major embarrassment. It would be expensive to go back and collect the data again. It would also be embarrassing to tell the patients about this, and so instead we're just going to impute the missing values. Don't try this in your hospital system. Okay, so sorry, this is a synthetic data set. Okay, so suppose that we try doing this using quadratic loss function for all these different kinds of data. Okay, so we're just going to take these ordinal answers, like what's your pain on the level from 1 to 7, and we're going to treat it like it's just the numbers between 1 and 7. Okay, and use the squared error to impute. Okay, and if we do that, we actually get, it looks like pretty good recovery. It looks close to the original. And the error is not too large. The green is 0 here. So a lot of this is green. It's doing pretty well, actually. If we use the appropriate loss function, right, the loss function adapted to the type of data. So for real values, we're going to use Huber because it's more insensitive to outliers. For the Booleans, we're going to use the hinge loss. And for the ordinals, we're going to use something I call the ordinal hinge loss. In this case, we get a recovery, still looks good. And in fact, the error is much lower. Okay. So it looks like using loss function adapted to the kind of data actually does improve outcomes, yes.
Why there's error on the Booleans that you're
I'm showing the, I'm showing the imputation error even from the ones that I observed. You can imagine here, what's going on is I'm trying to denoise my data. Okay, maybe this isn't appropriate in the medical setting, maybe it is, right? But you can still look at the difference between the value that you got and the original value that you saw. But you're right, it has a different interpretation.
So also how do you choose the rank?
Here this is synthetic data, so I know the rank. In general, I would suggest cross-validation.
Okay. I'm just wondering for the incomplete data, is it
Yes.
also true like when you increase your rank and the fitting error will be smaller? If
Uh,
don't consider the
Yeah, no, that's a generalization problem. right? So as you increase the rank, you'll always get an improved fit on the data in sample.
So even
right?
for the incomplete.
The in sample data, your fit will always improve and improve and improve as you increase the rank. You're increasing the model complexity. Now, the fit to the data you haven't seen might get worse, right? When your complexity gets too high because you've overfit. That's absolutely a phenomenon that happens. Weirdly, with adequate regularization, it tends not to. So there's this interplay between the regularization parameter and the rank. Yeah. But I cross-validation. Okay, so how does this work on actual data sets? So this is a yes.
Sorry.
Yes.
Just
Yeah.
a quick.
Yes.
So, is there any statistical theory or guarantee about with high probability the error is going to be small if not too much has been removed, not too much data has been removed?
There is for the various parametric families that I described before. I'm not aware of any statistical error guarantee in this setting. With this mix of loss functions, and I'm using actually the errors that I've generated here don't come from any parametric distribution, and the loss functions that I'm using are not negative log likelihoods of any distribution. Okay, but in fact they work better than if I used loss functions that were negative log likelihoods of some distribution.
But there are for certain parameterized distributions on the entries, you can prove that
Yes,
if you
that's that
get
template
this,
there. That's that template there that I went over
see.
quickly. Yes.
But I thought the template theorem says that you get something. Okay, no, yeah, okay. I understand.
Okay, you recover something
Yeah,
close to the
that's right,
super
that's
parameter.
right.
Yeah. Okay, so how well does this work on real data? And this is one thing I want to sort of show you that loss functions matter. Here's some hospitalization data. This comes from Stanford Hospital. Every row is a single hospitalization. We know some things about the demographics of the patients, their diagnoses, the procedures that were done to them, and their comorbidities, other diseases that they have. Okay, and here we're just using cross-validation, right? We drop out some of the data that we know. We fit the model on the rest, and we see what the imputation error is like on the data that we dropped out. Okay. And if we do this, sorry, this is too small to read. This yellow line, both these yellow lines are various different models with quadratic loss. These blue and pink lines are different models with other loss functions that are more adapted to the data distributions. And so you can see that as the rank of the model goes up, the number of features you include increases. That you're able to get much better fits in terms of cross-validated error with these adapted loss functions rather than quadratic. So the lesson here is that you should use a loss function that really makes sense for the error distribution, the kind of data you're seeing, not just use quadratic. Yes?
So those lines both keep going down?
Yes. Yeah, probably you should go to higher rank if you want to get good imputations.
Well, my question is, if you use PCA, do you still get as good an answer? You just use more dimensions, or do you never get as good an answer?
Here, PCA, do you mean matrix completion with quadratic loss, or
Yeah.
do you mean, okay. So if you kept going over here, well, eventually,
Because the test error doesn't have to get to the same place, and if it doesn't, that's interesting. And if
no,
it does,
yeah,
you
yeah.
compress it a little bit more, but you spend a lot more time doing it, and it's more complicated.
Yeah. I would be. Yeah, that's an interesting question. We didn't compute it for this data set. I would bet that you could get. I would bet that the minimum of the one with the adaptive loss functions is lower, but it's not shown by this plot.
Can you just tell us the size of the data set?
I don't remember. It was too long ago. I think it was something like it was in the tens of millions of patients. I'm going to skip this example because I really want to get to the theory at the end. Okay. Let me show you how to use this kind of framework to do dimensionality reduction. Okay. So here's an example of a problem. Suppose that we're trying to predict the number of labor code violations of various companies. Okay. These are companies in Ithaca, New York. You can see that this nursing home has committed many labor code violations.
Never gonna go with holiday.
Yeah, don't, stay away, right? Okay, so But this is labor code violations. This is like they're,
okay.
right? They're failing to pay their employees, or they're making them work overtime without paying them. I mean, it's bad stuff, but it's maybe not going to affect you as a customer. Okay?
Yeah, as long as your minibar is full.
Okay, right, but if we could do better predictions here, then enforcement action could be better targeted towards the companies that are doing bad things and stealing from people who probably don't have the economic clout to fight against it. Right. Okay. So among the information in this data set, there are 252 columns. There are 200,000 rows. Okay. And one of the columns is zip code, which I think is pretty interesting. Because you could imagine that there are cultures of violation and non-violation of labor code law in different geographic areas. Okay, but how do we treat zip code, right? How do we take advantage of that information? Okay, if I just treat this as a categorical variable and I do a one-hot encoding, then since there are 33,000 zip codes, I've introduced 33,000 new features into my problem, right? And there are actually zip codes in which there's only one business in this data set. Okay, so then I very badly overfit. Okay, so I want to use geographic information, but I don't know how to do it. Zip code isn't the right thing. Latitude, longitude is clearly not the right thing if I'm fitting like a linear model, right? The labor code violations should not be linear in latitude or longitude. Okay, so what do I do with zip code? So here's the idea: is I'm going to find another data set that has zip code in it. Okay, here where zip code is, think of it as the primary key of this data set. This is another data set that comes from the census. And so in every zip code, maybe we know the unemployment level, the mean income in that zip code, quality of the schools, some other stuff. Okay, but this is a sufficiently large data set. So 150 columns, one row for every zip code. I'm going to use the generalized low-rank model technique that we presented before with adaptive loss functions in order to compute features for every zip code. Okay, so the row of X I'm going to think of as a feature vector for the zip code. Okay, I'm going to show you the resulting embedding into 2 dimensions. But by choosing the rank, you can choose whatever dimensional vector features you want for these zip codes. Okay, so here's one embedding into 2 dimensions. You can see Cupertino and Sunnyvale, which are both in Silicon Valley, are close to each other in this embedding. East Harlem is about as far away as you can get from McCune, Kansas, which is this tiny city in Kansas. Okay, so I don't know, this is kind of interesting, but like, is it useful? Okay. So to figure out if it's useful, we're going to work with a 10-dimensional embedding. Okay, so 10-dimensional features describing each zip code. Okay, and I'm going to try 3 different kinds of models, right? And really, we're thinking about this as a feature engineering method. I want you to concentrate on how do we engineer the features that we're going to feed into our supervised model. Okay? So one way is to expand the zip code to a categorical variable using that one-hot encoding I described before. One is to concatenate these 2 data sets. So I'll join the tables on zip code. Right, so in place of the zip code, I'm going to put in all 150 demographic characteristics of that zip code. And the third is using these low-dimensional features. So I'm going to replace the zip code by these 10-dimensional, features that I claim describe the zip code. Okay? So notice the number of features here is much smaller than the number of features in either of these 2. Okay? And if I fit some kind of deep learning model using some automated machine learning techniques to choose the parameters, I'm really trying to be agnostic to the supervised error. You can see so both the training error and the testing error of the first 2 methods are much larger than that using these low-dimensional zip code features. Okay. So it kind of makes sense. So they're both underfitting and overfitting. Compared to the low-dimensional zip code features. By this, I think what's going on is that these 10-dimensional features really are capturing the right information about the demographics in these zip codes, right? That do a better job when you feed it into your other model. Okay. Yes, question?
Sorry, I thought you were about to answer this, but it looks like you're about to change topics.
I am about to change topics,
yeah. So does it matter which low-dimensional embedding technique you use?
It should.
Yeah.
It should. Yeah, I mean, this stuff isn't even a paper. This is just some experiments.
Yeah.
I think it's really intriguing. I don't know. I would love for someone to say something
I'll say
better
something
about
we did later.
which low-dimensional embedding, or what if you fit both models simultaneously, or there's a lot more to say statistically here that, yeah, I think it's relatively wide open. Yeah.
Do you try to replace zip code with real distance on the map, maybe weighted by population? Which will make
So
physical sense.
distance on the map, right? That's a graph notion, right? Whereas here I don't have a graph on the. I mean, I don't have a graph, right? It's a.
But whatever, you have this
Tabular
data
data
from somewhere. It's not
No, but what I mean is that every row corresponds to one zip code, not a pair
any
of
difference
zip
between
codes.
distance codes correspond to between in some distance in miles.
Yes.
Which is real measure
Yes.
to follows function.
Right, my loss function isn't over pairs of zip codes. It's only over single zip codes.
Suppose suppose a zip code and you have a real zip code,
Yeah.
and you know the distance between them because it's geographic.
Yeah.
It could use.
Yes. Yeah. Yes, you can. I don't think that that's the right metric because I think that what's relevant in this application is something like demographic distance rather than physical distance. And I think what's interesting here is that you've got some way of no, because for example, if you start in Ithaca, New York, and you go 10 miles in any direction, so Ithaca, New York is like as liberal as you can get, right? You go 10 miles in every direction, and it's full of Trump signs, okay?
Not any direction.
And then you go.
Stony Brook.
But Stony Brook is like that's like a 5-hour drive away. Right? I agree. If you go all the way to New York City, then suddenly it's very liberal again. Okay, but like distance, geographic distance is not a good proxy for demographic distance.
You can analyze it as population. Because New York is over.
Okay, these are interesting. So actually, the
sorry.
fact that we're having this discussion is a sign that there's more to do here, and I would love for someone to do it. Okay.
Well, Jason.
Yeah, good, thank you. Are there questions on this? No, I really think this is really interesting, right? How do you get the right feature representation for something like going outside your data set, like using a different data set to augment your data set? Okay. Yeah, this is the one I'm going to skip. Okay. You can do, if you use low-rank features to as control variates for causal inference, you can make all your causal inference methods perform better. That's what I skipped. If you're interested, then talk to me after. Okay, but I want to tell you about low-rank automatic machine learning because this is a crazy, weird application. Okay, so given n data sets and n machine learning models, okay, I want to be able to do anything that I want on this set of data sets and machine learning models, so that when someone gives me a new data set, I'm really good at figuring out which machine learning model is going to be an effective predictor on that data set. Okay, what's going to be the best supervised learning model on that data set when I fit into that data set? And I don't want to have to try out random forests with every possible value of the depth and every possible number of trees, and lasso with every possible value of the regularization parameter, and k-nearest neighbors, and I don't want to have to try everything. I don't have time for that on my new data set. But I'm willing to do a lot of work on this training set of data sets.
I thought that the new paradigm was to only try neural networks.
Yeah, why would I try to do it with